Hello, everybody. It's time to start our discussion on the stars. This will pretty much keep us on topic all the way towards the very end of the semester because there's a lot to cover about the stars. And what I want to do with this video is I want to introduce ourselves to the stars, get to know them a little bit. And then from there, we're going to have sort of a massive review of materials that we've already covered, but to put it into context so we can start charting the stars. How do we know where the stars are in the sky? How do we know their distances? How do we know how they're moving? How can we tell we live in this barred spiral galaxy and all the stars are rotating around this common center, the core of the Milky Way, where there resides a supermassive black hole? Really big task for this video, right? But hopefully you'll realize that it's not that complicated, especially with all the time we've spent building up our tool belt. I do want to start a little bit by just taking a look at a star cluster. We'll get to what star clusters are eventually, but it's just a nice region in the sky where we can see lots of stars. They all formed in the same place at the same time, and they're all associated with one another. But here you can see that there's a huge variety in stars. Some stars are bright, some stars are dim, some are red, some are white, some are blue. They have a whole large variety of properties. And that's going to be mostly what we're doing in Unit 2, Part 2, is trying to understand all the properties of the stars. So let's get to know the stars a little bit. And I apologize, let's just go ahead and put everything up since that last one didn't animate. So getting to know the stars. And we've already covered what a star is. This is what we talked about, the sun, but I just want you to remember that we are talking about the same thing. The sun is just a star, just like all the stars in the skies are stars. They're producing light by nuclear reactions happening in their core. For the majority of their life, that nuclear reaction is fusing hydrogen into helium. So what is a star? A star is a sphere of gas and plasma. It's that shape because that's the shape that gravity pulls it into. It's not collapsing or expanding because it's in hydrostatic equilibrium, and it's held together by gravity. The gravity pulling in matches the thermal pressure out, so it's a nice stable star, which gives it a well-defined radius. Something that's going to be a little bit tricky to figure out what the actual size of stars are. So if you go outside on a nice clear night, you can see about 4,000 to 4,500 stars, depending on what part of the sky you're looking at. You account for the other half of the Earth because you can't see through the Earth. You're talking about by the human eye, you can see about 9,000 stars. Once you start to use telescopes to make images brighter, you can start seeing a whole lot more stars. And then if you do some estimations, we can go all the way back to our very first lecture. You can come up with an estimate of about 400 billion stars just within our Milky Way galaxy. That is an incredibly large number, 400 billion. That's 10 to the 11th, 4 times 10 to the 11th stars just in our galaxy. But if you remember from our first video, we have a pretty good estimate for the number of galaxies that we have in the observable universe, which is about 2 trillion. That would be 2 times 10 to the 12th galaxies. And let's just assume that each one has about 100 billion stars on average. Let's multiply those numbers together. So we would have, let's just actually do the actual numbers. So let's take 4 times 10 to the 11th. So 400 billion times 2 trillion gives me an estimate of about 8 times 10 to the 23. Just so you can see how big that number is. Here's an 8 with 23 zeros after it. Number of stars in the observable universe. And our task is to understand them all. You might be thinking, what the heck, Dr. Lindsay? We don't have the time to go study each and every one of those. Well, regardless of this mind-bogglingly large number of stars that just exist out there in the observable universe, stars are stars. Physics is the same, the universe round. A lot of the stuff that we learned about the sun applies to all the stars because the physics is the same. The universe behaves in a well-organized way. If it didn't, if it was just random and every star was completely different from one another, science wouldn't be very useful at all because everything's just random. It's nice that there are these patterns, and the patterns are created by a number of physical mechanisms, the nature of the universe itself, which makes it so that we can actually understand all of those stars fairly simply. And we can do it by just looking at the essential properties and seeing how they relate to one another. So what kind of essential properties do we understand this mind-numbingly large number of stars in the universe and realize that they're all mostly the same rather than different? Well, the things that we're going to be after are luminosity. If you remember, that's the total energy production of a star. How bright of a light bulb is it? How much energy per second is the star giving off? That's luminosity. We want to know its temperature, which we know relates to color. Thank you, Wien's law and thermal radiation laws. We want to know their chemical composition, their size, their mass. And with those in hand, we can actually categorize the stars and see how remarkably similar they are and start building up a unified idea of how stars work in general. And we can do this with a high degree of accuracy and with our models, things like that are based off that standard solar model, the model of our sun. We can come up with sort of a standard model of stars. And now with all the observed properties, we have observational things to test our models of stars with. And if we have good models of stars, which they are remarkably accurate, then we can use those models and observations of stars in various at various ages, near birth, near death, in the main part of their life. And we can start building together an entire story of how stars form, how they live, and how they die. That's what we're going to be spending most of this semester on. And it all comes back to how do we determine these essential properties of stars? All right, big task. Let's start with one of the key things, because we really can't figure out any properties of the stars if we cannot determine the distance to them. Determining the distance to the stars is absolutely critical. Without knowing the distance to the stars, we're going to be lost from step one. So we better be able to determine the distances to the stars. You go at night, you see stars in the sky. Space is vast. We can't tell the distance that those things are away. I can't look at a star and go, yeah, that looks like about 30 light years to me. Maybe it is 30 light years, but what if that star is just really, 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 really bright compared to a star that's quite dim? The dim star at 30 light years could look just as bright as a bright star that's, say, 900 light years away. So we can't determine distance just by looking. What we have to do is we have to be clever, and now it's time to go back to review this idea of parallax. Remember that if you go ahead and stick your thumb out at arm's length and then blink your eyes, it looks like it shifts back and forth. And hang on just 1 second. Or you can observe parallax. So we can observe where, let's go ahead and put it. So we can observe where this appears on the background there. And then if I move my computer over some known distance, we can see that it shifts almost the entire width of the picture on my wall as I shift it back and forth. So that shift of where this looks like against the wall, you're observing the parallax. And objects that are closer experience larger parallax than objects farther away. So if you need a review of that, please go see the video on parallax, because we are going to be using parallax to determine the distances to the stars. How are we going to do it? We're going to observe the star from two different locations. Say we're going to observe the star at one point in Earth's orbit, wait 6 months and observe on the exact opposite side of Earth's orbit, on the opposite side of the sun. And we'll see how the star appears to change with respect to the fixed background of stars. Remember that how parallax works is it's inversely proportional to the distance. So if we increase the distance, we measure a smaller apparent shift. And you can do that with your thumb, hold it at arm's length. See how much it moves against the background. Decrease the distance by bringing it about halfway, blink again, and it'll look like your thumb is shifting back and forth. That apparent displacement with respect to a background gets larger. And I want to go ahead and demonstrate this. So here's how we might do an observation. So here we have a background of stars. Here's our nearby star. We're going to observe it from a known baseline, say the orbit of the Earth or the diameter of Earth's orbit. We'll observe it from one side, call that A, and it'll look like the star is hanging out with this star right here is hanging out over here. So that's where it appears amongst the background of much, much, much farther away stars. Then we wait 6 months and we take another observation from point B, and now it looks like the star is over here. It has an apparent shift. It looks like it's hanging out with different stars. And we can measure how much is shifted by using our angular measurements. So we can measure this angle, how much it shifted. Half an arc second, a tenth of an arc second, a thousandth of an arc second. Very hard to measure, but we can measure it. The stars are really, really far away, so this angle is incredibly small, less than an arc second. So then once we can measure this angle, notice that I've set up a nice right triangle here. We can just use a little bit of geometry. So I can go ahead and have this angle right here, which would be half of the apparent shift, what we call the parallactic angle, or usually if you look up a star's parallax, this is the number that's given. So you have this angle right here. I have the distance, what I want to know, and I know this baseline distance. So if you remember your trigonometry, which I'm sure everybody does and loves and uses it every day because you can use it to determine the distance to the stars, you can solve for the distance. The tangent of this angle, of the tangent of the parallax, so tangent of P, would equal the baseline. We're going to use the diameter of Earth's orbit. Half of that to get our right triangle here would be 1 AU. In this case, divided by the distance. And then I can say the distance equals 1 AU divided by the tangent of this angle, which I can measure. It's hard to measure, but I can measure the parallax. And notice that this is in red. I don't expect you to do the trigonometry, but you will have to solve for the distances. And that's going to be a good part of this video, is understanding how to solve for the distance. All right, so how do we actually do this? Let's actually take a look and revisit that unit we've been kind of ignoring, that distance unit, the parsec, because finally the parsec is going to become useful. Before I introduce exactly why is it the useful unit for determining the distance to the stars, let's take a look at this example over here. This is the measurement that we're going to make. So I had this cartoon right here, where what is our baseline? Well, our baseline is going to be Earth's orbit itself. So it's orbiting around the sun. And we're going to measure our nearby star, say in July, and see that it looks like it's hanging out over here with these background stars. Wait 6 months, so Earth is on the other side of the sun. A full diameter of Earth's orbit, which would be 1 AU plus 1 AU, 2 AU away, and would measure again, and now it looks like it's hanging out over here. On a view of a telescope, it looks like the star went from hanging out here to 6 months later it's hanging out here. We measure the angle, we can determine the angular shift, the parallax shift, and then that gives us our angle that we want right here. Okay, that all seems great, and I show you that the geometry works. So what is up with this parsec? Well, the parsec is the distance away, so how far away between our solar system and the star. A parsec is the distance away where you would measure this angle right here to be exactly 1 arcsecond. So it's the distance a star would be away to measure a parallax of 1 arcsecond. Parallax, PAR, of 1 arcsecond, SEC, smush those together and you get the parsec. That's how we actually come up with this unit. So you could actually do that. I could go ahead and assume that I know that this angle is, say, 1 arcsecond. 1 arcsecond is 1/3600th of a degree. So it equal, just calculate that out, 1 divided by 3600 equals 2.78 times 10 to the negative 4th degrees. I can go ahead and run through this. So the tangent of this angle would equal the opposite over the adjacent, 1 AU over the distance that I'd like. So I can solve for the distance would equal 1 AU divided by the tangent of 1 arcsecond measured in degrees, 2.78 times 10 to the minus 4. And out pops 265 AU, 206,265 astronomical units equals 1 parsec. Translate that into kilometers and you get about 3.1 times 10 to the 16th meters. So if you translate it AU to meters, or if you want to translate that to something a little bit more useful, you could translate that into light years, and you'd find out that 1 parsec equals 3.26 light years. That is a number you should probably go ahead and commit to memory. The 1 parsec equals 3.25, that's close enough, light years. Any question I ask, if you can remember 3.25, you'll get that question right. All right, so this distance, 1 parsec, is less than our closest neighboring star, which has a distance of 1.3 parsecs or 4.24 light years away, which means that even our closest star, its measured parallax is less than 1 parsec. The distance is greater, so the measured parallax would be smaller. So it'd be smaller in this case than 1 parsec, or it'd be smaller than 1 arcsecond, the parallax. All right, so now we know the general method. I've convinced you with a bunch of geometry that it works, and you're probably like, oh no, this is gonna be so hard. Don't worry, this simplifies, because the way that we're going to use this is a very simplified way. And this is why we like to use the parsec, because if we use the angle measured in arcseconds and we want the distance in parsecs, then the equation to calculate distance becomes super easy. So it only works whenever we measure the distance in parsecs, which has the symbol of PC, and we measure our parallax, this angle right here, in arcseconds. And when we do that, we have the distance equals 1 divided by the parallax. So I will give you the parallax, you 1 divide by the number that I give you, and you've solved for the distance. So the distance d equals 1 divided by this angle parallax p. That easy. So I did sweep something under the rug right here. There is a hidden math trick. You might be thinking, wait a second, wasn't there a tangent involved? Huh. Well, for very, very, very small angles, you know, like fractions of an arcsecond, that's pretty darn small. Then for very small angles, the tangent of theta is approximately equal to theta. It's called the small angle approximation. And it works out really, really well here. So notice that this is really just distance is 1 divided by the tangent of theta, but theta is about theta. Or so it'll be just 1 divided by the angle. Notice that's in green, you don't need to know that, but I have to tell you because it's a math trick that's there, which is not only interesting and cool, but I also want to make sure that you know that I'm not tricking you all. All right, let's run through some examples. So Alpha Centauri. We can measure the parallax for this star. It has one of the largest parallaxes that we can measure, and we get a parallax of 0.77 arcseconds. How do I calculate the distance? The distance is as easy as 1 divided by the parallax. I gave you that number, so just plug it in. 1 divided by 0.77 equals 1.3 parsecs. So now you've calculated the distance to Alpha Centauri. Not that bad. The hard part is actually making the parallax measurement. Once you have that done and you've done it well, you can determine the distance really, really well. All right, let's do another example. The star Betelgeuse in the constellation Orion. You could go measure the parsec if you're really, really, really careful and have the right equipment, or you could just look it up online if you trust the other people that already measured it, did a good job. And you'd see that it has a parallax of 0.0076 arcseconds. A much, 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 much smaller parallax, right? This angle is a whole lot smaller. And the fact that parallax is inversely proportional to the distance instantly tells me this star is really far away. The distance away is going to be much larger than the previous example. Let's go ahead and calculate it. The distance equals 1 divided by the parallax. So 1 divided by 0.0076 gives me 131.6 parsecs. So now I know Betelgeuse is 131.6 parsecs away. And again, just because we're not very used to parsecs, it's a rather new unit. Just to put this into something that is a little bit more intelligible, I went ahead and did this conversion for you where I converted from parsecs to light years, things that you don't have to do for this class. But 131.6 parsecs, there's 3.26 light years per parsec. So parsecs cancel, 131.6 times 3.26, 440-ish light years away. So when you go outside and you look at Betelgeuse, the light left that you're seeing, the version of Betelgeuse you're seeing is the version that Betelgeuse was 439 years ago. So it's 439 light years away from the Earth. Not that bad, but I want to make sure that you get this so you'll have plenty of practice on the homework that's going to be due. for the stars. It's a little while off after, so you'll get lots of practice. So I want to go ahead and do some here in this video as well. So here I have 5 different stars. And a quick question that I might ask you for, say, an exam or a quiz question is, hey, given these 5 stars, which one is closest to Earth? We've already done questions like this whenever we talked about parallax. But since we're reviewing it, so which one's closest? All right, so the bigger the parallax, the larger the measured parallax, the smaller the distance. So the biggest parallax will be the closest star. The smaller the parallax, the farther the distance. So the farthest star will be the smallest parallax. Okay, so which star is closest? I want to look for the closest means largest parallax. So which one is the largest? Which one? Vega. Vega is the closest star. Which one's the farthest? I'm looking for the smallest parallax. Oh, Naus. That is the smallest number I have listed. Okay, but now you can actually calculate the distances. So let's run through these. So I've given you, let's go to acrux. So the distance equals 1 divided by the parallax. The parallax measured in arc seconds is 0.01. So 1 divided by 0.01 is 100. The star is 100 parsecs away. So 326 light years. Aldebaran has a parallax of 0.5 arc seconds. Distance equals 1 divided by the parallax. 1 divided by 0.05 pops up 20 parsecs away. Antares has a parallax of 0.0059. This one's going to be pretty far away. Notice how small that number is. 1 divided by 0.0059 gives me 169.5 parsecs away from the Earth. Now, our farthest one, Naus, has a measured parallax of 0.003 arc seconds. So the distance would be 1 divided by 0.003 arc seconds. Gives me a distance of 333.3 parsecs, the biggest number I've seen so far. And then Vega, this one should be the smallest number, the one that's closest, because it's the largest parallax. So Vega has a measured parallax of 0.13 arc seconds. So the distance equals 1 divided by 0.13. And you get a nearby distance of about 7.7 parsecs away. Vega is pretty close. It appears really bright in the sky. It's not only a hot, bright star naturally, but it's also really close, making Vega one of the brightest stars in the sky. So 5 different examples. Hopefully by now you're convinced that this is fairly easy. It's a pretty easy equation to use. So now we can chart how far away the stars are, which is awesome. We can build a map of our local neighborhood. And as long as we can measure the parallax, we can measure the exact positions of all the stars that we can get a parallax measurement for, which is really, 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 really awesome. So this right here is a map of all the stars within 30 light years of the Earth. And how do we do that? Well, we just look at the direction so we know where it is in the celestial sphere. We measure the parallax. So now we know not only where on the celestial sphere is away, we measure the parallax. Now we know how far away. So we know what direction and how far away. So we can measure in what direction and how far away. The center of this would be, there's the sun right there. So we can measure what direction and then how far away, and figure out where all these stars are and build a map of our stellar neighborhood. That's really, 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 really cool. So in 1989, the European Space Agency launched this amazing mission called the Hipparcos satellite. And its job, the entire purpose of this satellite was to measure the parallax of the stars. and it measured the parallax for over 100,000 stars, 120,000 stars, and measured really, really, really precise parallaxes. So it charted out, it figured out where in our galaxy 120,000 stars were. And now we have an ongoing mission. Again, the European Space Agency is doing it. It's called Gaia, and it's getting close. It is measuring the parallax for 1 billion stars. This is the most accurate parallax data that we have. So there's been lots of updates to our distances. It can actually measure the position with an accuracy of 20 micro arc seconds. That's a distance of up to 50,000 parsecs away. So it's charting pretty much all of the galaxy that's within 50,000 parsecs of the Earth, where every star is. And not only is it measuring their position, it's measuring how that position is slowly changing, because the stars aren't sitting still. They move, they have motion. We just usually can't see it because they're so far away. But a long-term mission like Gaia with extremely accurate measurement of where a star is can not only measure parallax, but it can also, over time, accrue how that star is moving to build up its motion in the sky. And that's where we're going next. We can determine the distance, but we can also determine the star's motion. The distance is key for this one. But what we can do is, yes, it takes a lot of time to do these types of observations, because to us, the stars look fixed. They don't really look like they're moving, but they are moving, and they're actually moving pretty quickly. It's just for us, they don't look like they're moving at all because they're so very, 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 very far away. Most of them are tens of thousands of parsecs away just within our galaxy. Here is the star that is moving the most in our sky, Barnard's star, and we have measurements 22 years apart. So the trick here is you have to find the one thing that changed. So here's our pattern of stars. 22 years later, looking at that same patch of stars, you have this dot right here that moved from here, oops, don't hit a button, up to here. It actually moved. You're seeing its actual motion in the sky. So this motion that we measure across the sky is what we call proper motion. It's just how far did it move in the sky over a certain amount of time, because we're talking about motion, so we need a distance and a time. Again, if we don't know the distances to the stars yet, all we can do is measure how much of an angle it changed by, and then we can say over 22 years, we can measure how many arc seconds it moved over 22 years to figure out how many arc seconds per year it moved on the sky. So we measure proper motion in things like arc seconds per year, or often milli arc seconds per year, because they're really not moving very much at all. A very hard measurement to take, but all it does is it takes a lot of time, a good amount of time, and really, really precise instruments like the Gaia satellite. And we can measure the proper motion. We can see how it's moving. But notice this is in milli arc seconds per year. I'd really like to know, how is that star moving? How are the stars just in general moving in the Milky Way galaxy? What is that in like miles per hour? What is that in kilometers per second, meters per second? And for that, we have to do a little bit of work. We want to measure the star's true motion, as we call it, how it's truly moving in space. Then we got some work to do, because what do we see from Earth? So here's our solar system. And let's say we have stars, and we measure it at one time, and then we wait, say 20 years later, and it looks like it's moved from hanging out with these stars over here to hanging out with these stars over here. So what we observe is not its true motion. What we observe is we're observing its transverse motion when we take that kind of measure. When we make this kind of measurement, we're observing its transverse motion, its side-to-side motion, which is great. It's really hard to do. This kind of work is called astrometry, but you can measure that transverse motion. So our proper motion in arc seconds per year, what we'd like to do is actually translate that into how fast miles per hour is kilometers per second, what we call as true transverse motion. And we got some work to do. If we wanted to actually figure out how fast it's moving or how far it moved, those two things are going to be related. We're going to have to first figure out the distance to make these sort of translations from a proper motion to true motions. We also, to a component, we can see it moving this way, but we can also measure its motion towards or away from us. Notice that it has both of these components. It has a transverse motion component, and it's got a radial motion component. You put those together and you get its true motion in space. It's true motion. How can we get radial motion? I can't actually see if it's coming right towards me. It looks like it's always hanging out with the same stars. Oh, wait, Doppler effect. We can measure the Doppler shift to determine the radial motion of the stars. Look, if it's blue shifted, it's moving towards the Earth. If it's red shifted, it's moving away from the Earth. How much one of those spectral lines moves from its rest wavelength can translate to its actual true velocity in space. If it's moving, say, 20 kilometers per second towards us or 20 kilometers per second away from us, 30 kilometers per second towards us, 30 kilometers per second away from us. So the radial motion, we just use the Doppler effect. And we put all that together, the distance, so we can translate what its proper motion is to a true transverse motion in kilometers per second or miles per hour, if you like. We do a Doppler measurement to determine its radial motion, it's towards or away from the Earth. And then we can use the Pythagorean theorem. You're going to draw this right triangle here to figure out its true motion. It's a lot of work, but we can then figure out how not only where all the stars are, but how they're moving. And once we know their distances and their true motions, this really builds a very, very dynamic map of, say, the Milky Way galaxies, because we can see how all the stars are moving in concert with one another according to Kepler's laws, with a little bit of modifications by Newton and a little bit more know-how. But now we can map out the stars, where they are, so we can start getting the shape of our galaxy, how they're moving, how it's changing. And we can use all this to determine that we are living in a barred spiral galaxy, which is really, really cool. This is how we determine, say, the shape of the galaxy that we live within. Now I want to go ahead and show you, since that's measuring this true motion is a little bit confusing, hopefully a little bit of an animation will help. So here we are at Earth. I've put the orbit of Earth just to remind us that we would measure the distance by doing a measurement here and then 6 months later. This is grossly exaggerated because the stars are light years apart, and this is 1 AU right there. So this is grossly exaggerated. I just want to show you how this all works. So we want to see how this star is truly moving. The first thing we have to do is determine its distance. How far away is it? Well, we can measure its parallax, so do a measurement here, wait 6 months, do a measurement here, and measure its parallax, translate its parallax into distance. This distance equals 1 divided by the parallax, and that gives my distance in parsecs. So now I have that, which is a key part of this. Once I know that, then what I have to do is, over a long period of time, see how the star appears to move. We see this orange motion right here. This is how it appeared to change with respect to the background stars. We see the transverse motion from Earth, how it's moving through the stars. So I'm going to do this again. What we want to know is its true motion, how it's really moving, which is a combination of not only this transverse motion, but its radial motion. So the transverse motion, it's like the image that I showed you where you compare two images taken at a long time interval between them. You look to see how much the star has moved, and you translate that knowing the distance from how many, say, arc seconds per year is moving to how many kilometers per second or miles per hour is moving. So our transverse motion is measured by astrometry, seeing how it moves, measuring how many arc seconds per year it moved, and also knowing the distance so we can go from a proper motion of arcseconds per year to a transverse motion measured in, say, kilometers per second. The radial component is fairly easy. Just do a Doppler measurement to determine how much is moving towards us or away from us. Notice that I've colored this one blue because it's moving towards us, so its spectral line should be blue shifted. The combination of these two motions is the true motion, or rather, a different way to think about it is this true motion can be broken down into these sub-motions. And all we have to do is just use a little bit of geometry, and then we can calculate the true motion. And you by no means have to do this, but I want to show you how it would work. So you measure its proper motion, how many arcseconds per year. You know its distance, so then you can do a little bit of geometry to figure out arcseconds per year translates to, say, 24 kilometers per second of motion in the transverse direction with respect to Earth. You do a spectroscopic measurement to see that H alpha has moved away from its rest wavelength to shorter wavelengths, and how much it's moved by translates to a radial motion towards the Earth of 20 kilometers per second. So now I know this component, 20 kilometers per second, this component, 24 kilometers per second. I know a squared plus b squared equals c squared. Thank you, Pythagorean theorem. So a squared plus b squared equals c squared. That means c would equal the square root of a squared plus b squared. I can go ahead and calculate that out. That's its true motion, equals the square root of 24 kilometers per second squared plus 20 kilometers per second squared. Crunch those numbers out, you get 31.24 kilometers per second. That's the star's true motion. So just with a little bit of know-how. All right, I know this video had a lot, but this is foundational stuff. What I'd really like for you to take away from this is that we measure the distances to the stars using parallax, and that once we know the distance, say via parallax, we can actually measure the actual motions of the stars by translating a proper motion and a Doppler measurement, a radial motion measurement, into a true motion measurement. All right, so first step, we have charted the stars. We know where they are and we know how they're moving. We'll pick up with more properties of stars in the next video.